All right, so let's take a look at this. We have it's actually on CPU organization. So as we are going through this, we'll be diving more into the ISC, like what informs the ISC of any particular processor, right? So we'll be doing some introduction. You might already have knowledge on instruction formats. How do you call it? Zero address, one address, two address instruction, things like that. You already have knowledge on that. You also be might see why certain addressing modes are required. You also might see types of instruction and generally the instruction cycle in general. So let's start. So as we are going through this, I would like you to take note of the single bus organization, right? We'll see what it means later. Register transfer, control sequences, memory access, control sequences for execution, multi-bus organization, control unit, stack organization, and subroutines. Alright, so far every processor we deal with it just fetches one instruction at a time, at least from what we've done previously, right? And instructions are fetched from successive memory onto a branch. Simply like this. Usually in memory you just have the all the instruction, I mean in von Neumann considerations, right? You have all the instructions stored in memory, right? So if you fetch from here, we'll come and fetch the next one from here, the next one from here, like we'll go successively, right? But this works until we meet certain instruction we call branch instructions. Branch instructions are quite different, right? They kind of allow us to move from maybe 1 to 3, right? And that's the whole point of branch instruction. They are like your if else statements, yeah, something like that. So the processor has to keep track of the address of the memory location containing the next instruction to be fetched using the program counter, right? So supposing the program counter fetches from 1, right, it will now be storing the address of what, 2, right? So the program counter will now store the address of 2 because it previously fetched from 1. Then yeah, so P will be equal to, let's say, 2. The address of 2, let's say the address of 2 is something like 0x0, let's say 1, and the address of 1 is 0x00, right? So the program counter will be storing like 0x01. This is just abstract, right? It's not the real thing. Yeah, so something like that, right? And that's what the program counter will be storing. So when it fetches from 1, the program counter will now update itself and store what, 0x01, right? So that the next time it comes, it will fetch exactly the next instruction above it, continuously like that until the program end. Now, after fetching from memory, instruction is stored in the instruction register for decoding. Basically, that's all what computers do. Basically, you fetch instruction, decode, and execute it, right? So any instruction it fetches, it goes to the instruction register. Then the instruction register is somehow some way connected to the control unit, and in the control unit, your decoding is done. Now, assuming that memory is byte addressable, right? So we are assuming this condition that memory is byte addressable. What we actually want to achieve is a realistic view of how real world microprocessors work, right? You see, usually we're doing PC+1 from the previous lessons, but the truth is, you can't really store in 8 bytes, like a full instruction 8 bytes, right? It was a whole problem. Remember the question where you had to do multi-cycle fetching for just a load instruction, right? It's quite hectic to wrap your head around, especially even for the programmer. So the architects do is they encode the instruction in 4 bytes, right? So that now instead of moving +1 +1, you'll be moving +4 +4 in memory, right? And this is actually quite a great gain, and we'll see that. But yes, so supposing memory is byte addressable and each instruction comprises of 4 bytes, then increment of the contents of the PC, we increment the contents of the PC by 4, right? So as you can see, PC will be equal to PC +4 from here. Now we carry out the operation specified by the instruction, right? So it means that after we fetch the instruction will be decoded, and based on the decoding, the signals will be activated, and the signals will execute that instruction for us. Now, from what we have said above, this is a general processor to conceptualize it, right? So this is a processor, but this processor is special because it has only one bus, right? One bus in the sense that, listen, no two registers are connected directly to each other, right? What it means is that anytime two registers want to share value or share data, or yes, write or read data from each other, they all have to use this single thing in the middle, right? So this is the bus, and the truth is it's quite a problem because it means that there will be kind of a contention. Some have to wait for um, the usage, right? So generally there are two subunits within the processor. Generally every processor has the control unit and the data part. Now the control unit is usually not shown here, yeah, because it's usually just um, logic controlling the sequence of events, right? But this is the data part, and the data part is actually the components which handle the flow of data, right? So this is the data part, and what you see in blue actually from the control unit, or usually to the control unit, right? Physically, there's hardly any difference between the control unit and the data part. Hardware of both side units are tightly coupled together into a single physical unit that forms the CPU actually, and the data part includes the internal part for the movement of data within the processor. It includes registers, other hardware, temporary storage like latches, multiplexers, demultiplexers, decoders, among others. Other buses are external buses that connect the memory and I/O devices. So it's just trying to describe the control unit and the data part. But the main concept you are supposed to see here is that there is actually a bunch of registers and also a bunch of components, right? But these components are activated or controlled by signals from another unit called a control unit. Now, these components, when connected together, form the data part, but the signals which activate them come from the control unit. So we would understand it later. Now, the ALU and all registers are interconnected via a single bus. This bus is external to the processor and should not be confused with the external bus that connects the processor to the memory and I/O devices. What is saying is that in this single bus architecture we are talking of, right? Remember, we are dealing with single bus organization. The ALU and all other registers, so the PC, MAR, like the Y, this IR, they are all registers, right? But you see, they are all interfaced by a single bus, right? They all interface by a single bus. So maybe if you want to move some data from R0 to Y, it means that first you have to pass it to the bus so that Y can pick it, right? There is no direct interconnection between RO and what Y. They all have to use what this single bus. Now that fixes that, and the data and the address lines of the external memory bus are connected via the data processor, the memory data register, and the memory address register respectively. Okay, so the truth is the first part actually explains the concept of external and internal buses, right? So it's saying that this bus you see here is the internal processor bus, but there is another bus which actually is interfaced somewhere here, right? And that's the external bus. The external bus can be from maybe your storage device, right? But the internal bus is for sharing among the elements in the processor. So the data and address lines of the external memory bus are connected to the internal processor via the memory data register and the memory address register. Like I said, the external bus is connected via these ones, memory address register and memory data register. We understand why, so let's keep on. The input of the memory address register is connected to the internal bus and its output is connected to the external bus. Here's it. When we want to fetch data, right, we put the address of the data into the memory address register, right? So the input has to be what in the internal bus. Now the address which you are going to read from the memory address register has to go and activate it in memory. So the output of the memory address register is connected to what? The external bus, right? And the external bus will pick it and read it from memory. The Yes, the number and use of processor registers R0 through to Rn-1 vary from one processor to another. We'll see what that means by just saying that some registers are special, some are not special, right? So this R0 to Rn-1, any R you see there is a register, but some processors actually have special uses for them. Some they don't. You can use any register anyhow you want. Right now, three registers YZ and temp are transparent to the programmer. They are used for temporary storage during execution of some instruction. What it's trying to say is that in this architecture, right, the processor which is available and the registers which are available to the programmer are R0, R1, R up to Rn-1, right? But there are some registers which are not available to the programmer, right? And they actually um, three of them. We have this Y, we have this Z, and we have this temp. Usually, they will define for you which ones are transparent and which ones are not transparent. Transparent in the sense that there is no way the programmer can access them, but the CPU uses them in its calculations. So we realize why. And we have one last line. So it says the multiplexer selects either the output of the register Y or the constant 4 to be provided as input of A of the ALU. This is what it's saying. You see this is a multiplexer here. Now you can either choose to select from the constant 4. So means that the input 4 or the output coming from the register Y. Yes, and this is usually part of the explanation of the architecture. You realize that in this architecture we are doing PC is equal to PC plus 4. We are increasing PC plus 4. So 4 is something we'll be using frequently, right? And if 4 is something we'll be using frequently, then we'll like to store it somewhere or always apply it somewhere, and that's what you see. Then the register Y is also to store one of the operands we'll be using in calculations. Realize that in this architecture, we only have a single bus, right? But our another problem is even with a single bus, we always need two operands. This is not an architecture which has some internal register for saving resource or something, right? So we only have a single bus, right? So we need this register to store one operand, and the other register, the other operand will be in the bus at the time, and it will come through B, then be used. So this one of the operands will be in Y, and it will flow into the multiplexer. We can select it so that finally it will come here, right? But we'll see a clear example, so never mind. Now the multiplexer selects yes either Y or the constant 4. The instruction decoder and the control logic is responsible for implementing the action specified by the instruction loaded into the IR register. So at a point you might be asked to completely show what happens in a processor, right? And in doing that, you have to at a point put some of the part of the instructions you fetch into the IR register. Now it is the job of the instruction decoder and the control logic to take this instruction you put there, take the the necessary bits and decode them and allow it to be like activate the correct signals. We'll explain it better later, but basically that. So let's look at register transfers. Now we already realized that in our architecture here, we only have a single bus, right? And that's like a big problem, right? So to deal with it, then we have to have some mechanism, right, to control who gets access to the bus and when, right? And we use kind of a tri-state buffer, right? So we have a signal called R in, right? And we have a signal called R out, and Ri is the register, right? So we are assuming that Ri is a general register, and the R in and the R out are signals coming into the register. Now we are assuming that R is any general register, yes, and R in R out are signals coming to the register. We're also assuming that this X is some tri-state buffer where when RI in is 1, it will turn on, and where RI in is 0 to turn off. The same thing for R out. So let's make progress in some reading. It says instruction execution involves a sequence of steps in which data are transferred from one register to another. Yes, and you'll see that a lot. But let's continue. For each register, two signals are used to place the content of that register on the bus or from the bus to the register. This is what it's saying. It's saying that either ways, right? Sometimes we'll be writing from the register to the bus. Other times we'll be writing from the bus to the register. So we can have from the bus to the register or from the register to the bus, right? And now it is these control signals which allow us to do that, right? So the inputs of register RI are connected to the bus via switches controlled by the signals RI in and RI out respectively, right? So these are the control signals. And when RI in is 1, the data on the bus is loaded into RI. What this means is that, assuming there is data on this bus, right, and you say RI in to be 1, that data will flow from the bus and it will be entered into the register. Now, the inverse is that when there is data in RI and you set RI to 1, and that data will flow from what? RI, and to go to the bus. And it says all operations and data transfers within the processor take place within precise time period defined by the processor clock. So yeah, that means that everything is clocked somewhere or somehow, right? Then we are going to see control sequences. So far we've seen our architecture that we have been faced with, right? Single bus, there is kind of a bottleneck. Two people cannot be writing to the single bus at the same time because the data will be corrupted, right? And it will also take some signals for us to write to the bus or read from the bus, just like we saw here. Now the last part is this part, how we can actually, so we are now looking at this architecture, how it will affect us when we are kind of, let me say, programming from a higher level, right? So assuming that you are the programmer now, and now you know how the computer is arranged at this level. So you want to write code, right, to do any operation, right? So then because of the arrangement of elements within the architecture, it will affect how the code you write, the code you can also write, right? Because due to the architecture, there are certain commands you cannot give here, right? And there are certain commands that you can give here. So we'll consider that. So the ALU is a combinational circuit. It has no internal storage. That is what you have to put in mind. What it means is that anytime you use the ALU for an operation, take note, you must make sure that Z in is turned on so that the ALU can store simultaneously. Like immediately it finishes, it will flow into Z in, right? Because the ALU cannot store, right? If you don't do that, I mean, you will lose your operation. So if you don't do that on the same cycle, you lose your operation, and we'll see that in a bit. So let's take our time. So let's assume it says a sequence of operations to add the contents of register R1 to R2 and store the results in R3 is shown below, right? So let's see, the RI here is representing register. It can be any of the registers, R1, R2, R3, R4. Like it's just saying like any register in our system, right? It's located somewhere here. So let's see how we can do that. We want to add R1 and R2 and store the results in R3, right? Now I already told you that in this architecture we are faced with a problem, and the problem is that we only have one bus, right? So because of that, it means that our operands, some way somehow, they both have to arrive at the ALU at the same time, right? To make that possible, they have provided another register that we can temporarily use to store one of the operands, right? So that while one operand is in the bus, right, at the moment, it's applied at the bus at the moment, the other is also applied in the register, because we can't activate two registers at the same time. Why? We only have one internal bus. So what we usually do is, the first step is we'll try to store one of the operand, and in this case the question is actually trying to store R1, right? So they will say R1 out, Y in. What does it mean? When it says R1 out, it means that write the content of R1 to the bus. So that content will flow, right, and it will appear here, to appear here, right? So to flow several places, right? Now the only place it will go next is Y. Why? Because it is Y is the only part who has activated the write signal, like write the data from the bus into my register, right? So that's one part. Now the next part is R2, right? So now we have R1 stored in this register. So R1, the value in R1 is stored in this register. We don't know the value. Then the next part is R2. So what we can also do is we can say R2 out, right? Now, like R1, R2 will also flow to several places. So to even flow to Y, it will flow to B, right? Several places. However, the issue is Y will not pick it, because in this line we are not saying select Y. We are not saying Y in, sorry. So Y will not pick R2, right? But R2 will also appear at B. So the R1 we applied previously, and we'll stop applying it, because we've come to another cycle when we are now applying R2, right? So now in the bus, R2 is in the bus, and R2 gets to B. Now we also have to do in the same cycle, in the very same cycle. Realize that the CPU does things and everything is in some cycles, right? So in that very same cycle, we have to select Y, like we have to activate Y, so that Y will also get to A, because the ALU needs two operands, right? Now, as saying R2 out will bring the operand R2 to B, because B is directly connected to the bus, and as saying select Y will bring the operand R1 to A, because the mux is connected to the constant 4 and R1, right? And now when we select Y, then it would appear here, right? And I was even thinking if there will be another signal called Y out, right? So that Y will output a signal, Y will output data here, but it's okay if the question did not provide a signal for Y out. But it's also something you should take note of. Then the last part is add. Now this add is an instruction coming from the control unit. You see, they didn't show it here in the diagram, but remember from here, you realize that there were some control signals, right? This is coming from the control unit, right? And that's what you see. So add, right? Now you also have to activate Z in. Why? I already said it. Anytime you are using the ALU, right, immediately you do an operation, add, subtract, or anything, you have to say Z in, or you have to activate Z in, so that the results will be stored. Otherwise, you will not get the results. Now this is all done, right? Now remember, we want to add R1 and R2 and store the results in R3. So the issue is simple. Now we have R1 and R2 added, but the result is stored in Z. So we want to move it from Z into what? R3, and it's easy. All we have to do is say Z out, so that Z will move its data onto the bus, and we'll have to say R3 in, so that in the same cycle, R3 will also allow for the writing of the signal onto its bus and onto its register. Then we are done. So with this sequence of instructions or procedures, we have been able to successfully add R1 and R2 and store it in R3 using this architecture. Very procedural. Now the next part happens when we are fetching from memory. You realize we had MAR and MDR, but there was some problems associated with it. You were saying the MAR is the input of the output. Yeah, the input of the MAR is connected to the internal bus. The output is connected to the I think memory, and yeah, things like that. So this is actually what is explaining it. So you have the memory bus, and now this is for the external memory, right? So this part is for the external memory, The red one is for the external memory, right? The bars for the external memory, that is where when the external memory goes to pick data, it will put it. And this is for the internal bus, that is where the internal bus puts its data, right? Now, the one who is interfacing the two of them is called the memory data register. He's sitting there like the middleman, right? Now, you realize that this is how we go about. So to fetch a word from memory, the processor has to specify the address of the memory location, right? So the address into the MAR, right? To do that, yes, when the address comes into the AR, then to issue a read operation, and the data will come to the MDR. This is what it means. You see, to get something from memory, let's assume that this is memory. I don't like drawing up on this, but let's assume that this is memory. Right, memory has several locations. Now, the truth is, several locations. Maybe we only needed here, right? This location. We only needed to read from this location. So we will need the memory address register to specify the address of this location, so that this location will be selected in memory. When it is selected, its data will come and pour on the external bus, right? Now, when it pours on the external bus, we issue a read operation, right? Now, the read operation comes along with 4 control signals: MDR in, MDR out, and we also have the external part called MDR in external, MDR out external. So, assuming the data is on the external bus and we want to pick it into the MDR, we'll say MDR in external, right? Will allow it to pick the data from the external bus. So that data will become stored in the MDR, right? And now in that case, if maybe you want to transfer it to another register somewhere, or any other location, like any other location on the internal processor, like from the MDR to any of the internal processors, it's possible. Why? Because now it is for memory, we have it in a register which is directly connected to the internal bus, right? And that's basically it. So it comes with a bit of complications, right, when we bring the external cases. But just take note of this diagram. Realize that there is some part where we allow output external, input external, MDR out, MDR in. We realize that this part, it was already part in the original diagram, right? But this interfacing is the new thing, the only new thing is. So we'll take note of it. Now, they said during memory read operations, the timing of the internal processor must be coordinated with the response of the address device on the memory bus. The processor completes one internal data transfer in one clock cycle. The speed of I/O operations are slower than the processor speed, and also different device speed is different from each other. To accommodate this, the processor waits until it receives an indication that the requested operation is complete. A signal called the memory function complete is used for this purpose. During read or write operations to or from memory, the other operations wait for the memory function complete signals. Wait for memory function complete signal is a signal that causes the processor control circuitry to wait for the arrival of the memory function complete signal. So let me explain everything. What he's saying is that, listen, when we come to the internal bus side, that's this part. When we come to the internal bus side, the speed here doesn't correspond to the speed on the external bus side, that is IO, right? So it doesn't correspond to the speed. So since it doesn't correspond to the speed, we can't be thinking that, oh, we are fetching data and exactly in the next cycle we are going to use it in addition, because maybe exactly in the next cycle it hasn't arrived, right? So to do that, there is also another special function called the memory function complete, right, which is used to signal the control units that, oh, we finished the operation now, the data is available in the MDR, so you can pick it up, right? Now, they say that during write or read operations from memory, the other operations wait for the memory function complete signals, right? So it means that during that line of operation, right, we'll have to like keep the other signals on and wait for the memory function complete signals like to be on before we complete the operation, and we'll see that in the example, so never mind. Now it says the write memory function complete is a control signal that crosses the circuitry to wait. Yes, so you realize that the speeds are different. So it means that one has to wait for one, right? And in this case, it's the control, the internal one which has to wait for the external one, right? And the external one does it by executing this instruction, this here signal, the wait memory function complete signal. So let's see an example. And in this example, it says we are going to consider an instruction move R2 move into R2 the address specified by the memory location in R1. It's confusing, but listen. What he's saying is that we have specified an address in external memory, right? But that address, the value of that address is stored in R1, right? Now, what we want to do is that we first want to go and fetch that data, right, and move it towards into register R2. And remember, register R2 is on the internal side, right? But the address specified in R1 is on the external side, right? So when you see these differences, you realize that then we are going to need some wait memory function complete somewhere in our whole operation. So we will start. Now this part is just defining like what we will need to do, right? So it's like our guiding principle. So we start by realizing that first we have to put the address into the memory address register. One thing is, no matter how you don't even remember these things, remember that once you specify an address to fetch a data, right, we will have to put the address into the memory address register to go and fetch the data. Like that's the very first thing you should do. So the very first thing is the address specified in R1, the address which is stored in R1, we'll put it in the memory address register. Then we'll start a read operation. Once we start a read operation, we'll wait for the memory function complete signal for the read operation to come, right? Then after the memory function complete signals brings it onto the external bus, we can load it from the external bus into the onto the external bus. You can load it from the MBR to the memory bus, right? Then now we'll put the content of MBR into R2. Now this one is like some internal operation. The rest some way somehow consists of some external operations. So let's see how the whole sequence is going to be. So the first part, you want to do this. You want to put the address specified in R1. That square you see, it means that there is an address specified in R1. It is like indirect addressing, some kind of register indirect addressing, right? Something like that. So the address specified in R1, we are going to take that address and put it in the memory address register, right? So that whole operation is specified in this line, right? So we are first going to say R1 out. Why? To put the content of R1 onto the bus. Remember this bus? To put the content of R1 onto the bus. And we are going to say MAR in, so that MAR can receive the content of the address on the bus, right? Now, once we do that, we execute a read operation, right? And now, yes, it's true, we'll do it in the same cycle, right? Because like none will affect each other. Now, in the next cycle, we activate MDR in for the external side, right? So we say you MDR be ready to receive data. Now we wait for memory function complete. So when the fetching is complete and the data is collected from memory, it will come to this bus and the MDR will take it because it has its what in the external signal input what activated. So it will take it. Then now we've realized that after this line, after these two, the data we needed to go and fetch from the memory, right, is now stored in MDR. So the next part is just moving from MDR to R2. You realize that MDR and R2 are connected to the same internal bus. Like you see, they are connected to the same internal bus. R2 will be somewhere here, right? They are connected to the same internal bus. So it's just a simple operation. We'll just say MDR out, then R1 in, R2 in, sorry, I think R2 is the one taking it. So we'll just say MDR out and R2 in, and as simple as that, we have been able to transfer data from memory into the R2 register, right? So one more time, we wish to read from memory, right? Now the address specified in memory is stored in what? Register R1, right? Then it means that we have to go to memory, fetch that data at that address, then come and put it in the MDR before the MDR can give it to whoever needs it, right? So in this case, R2 is the one who needs it. But before we can go to memory, we have to contact the MER. It is like the MER which interfaces with memory. Like MER is the one who like specifies kind of the memory location we want to read from. So the address specified in R1, we'll put it in MER, right? So that's what this line is doing. So we'll say R1 out, right? So that R1 will pour its data onto the external bus. Then we'll say MAR in, so that MAR will take the data on the external bus, on the internal bus, sorry. I think this diagram should be here on the page, but it's okay. So R1 out, MAR in, right? Now, once we do that, we have somehow been able to get the address we are specifying into the memory address register. Now, once we have the address in the memory address register, we can execute the read operation, right? And that all can be done in the first cycle. Now, in the second cycle, we make sure that the memory data register is ready to receive. So we say what? MDR in external, because the data that MAR is going to allow us to read will come and pour on the internal bus, and it is only the memory data register who has the capacity to receive from the external bus, right? So the data that MAR is going to read will pour on the external bus, right? And it's the MDR register which has the capacity to read from the external bus. And to read from the external bus, we say MDR in external, right? So it means that the external input, this one, right, we should allow it so that it will take the data from the bus here, right? But the truth is, you see, immediately we execute this read operation, it's not that same time that the data becomes available to the bus. So we have to wait, right? And in waiting for that, we use the wait memory function complete. Now, once it comes on the bus and MDR takes it, right? So at the end of this line, we are assuming that we have waited the necessary time and we have finished that operation and MDR has been able to take it. So once we have been able to do that, then we go to the next step, right? And the next step is just transferring it's like just transferring data from what? MDR to what? R2, right? Because it's not like the data we needed from memory, we have been able to manipulate and get it into what? MDR. Now we need to transfer it to R2, and it is just this one line, MDR out, R2 in. And with that, yes, you are done. You have been able to get data from the address specified in R1 into R2, right? And that is that. So there is also one last example, and I think this will cut it. So it says we have to consider the instruction. We are supposed to move data from R2 into an address specified in R1. The first one, we're supposed to move data specified at an address in R1 into R2. Now, this one is different from this one in the sense that, you see, anytime basically all architectures, right, the first register is called the destination and the second register is the source. I don't know why they do it like that, but that's what most architecture do, right? Now, realize that here the destination is R2, it is internal, and the source is what? R1, it is external, right? But realize that here the destination is what? R1, right, with a square around it. But you see that it is in a box, so it's external. It is specifying an external address, and the source is what? R2. It is also but it's what? Internal, right? Because there's no box around it, right? When there is a box that square brackets around it, right, it is specifying an external address. So it's the same process again. The first step, we need to read from memory, right? Like we need to, you see, this time we actually writing to memory, right? Because we are moving R2 into the address in R1. right? But the first time we were actually moving from memory into R2, right? So those are different. Those are different. One is like a read operation, one is like a write operation, right? So to do this, generally, since you see the square brackets, the first thing that should come into your head is, oh, one way or the other, we are going to use the memory address register, right? Now, the address that the memory address register needs, it's specified in what? R1, right? And that address is an external address, so it's like some in the indirect address or something like that. So that address, you take it from R1 and put it into MAR, right? Now, once you put it into MAR, it is like you execute a write operation. This one, you execute a read operation because you are moving from the external memory into the internal memory. But here, you are moving from the internal memory, which is R2 because there's no square around it, into the external memory. So this is a write operation, right? So that's why it says start a write operation, right? Now, remember, when we want to write, this R2 is not directly connected to memory. It is what? The MDR, which is directly connected to memory, right? So this one will specify the location we want to write to, and this line will specify the location, the data we want to write. So the location is different from the data. Take note of that. So now here's the real deal, right? This one is just explaining. So the first one, we first have to say R1 out, MAR in. Why? The data specified in R1 refers to the memory address location that we wish to write to, right? Now we have to activate it with this one, right? Now remember, you see in the first one when we were doing the read, in the very same cycle we had activated the read signal, but this one we can't activate the read signal because our data is not yet in the MDR. It is the second cycle which brings our data into the MDR. So you realize that we can say R2 out, MDR in, write, because now our data will now be in the MDR after this signal, right? After this cycle. Then we now have to execute the wait memory function complete because the write operation takes some time, right? But remember, the wait memory function complete is because of this write operation, right? And now, where are we taking the data to write from? We are taking from MDR. So we have to activate the MDR out so that the MDR will write the data which it took from R2 onto the external bus. So that when the memory is ready to pick data, it will just pick it from the external bus into memory. So that's it. So those two questions are actually different, right? One was actually reading from memory into register. One was actually taking from register into memory, right? And both of them have interesting use cases.